Okay, so in the previous classes we have looked at oblique shocks and expansion waves. So, oblique shocks are compression shocks, they are at an angle to the flow, they turn the flow towards itself, while expansion waves are more gradual, they are isentropic and they turn the flow away from itself. So, if you take any particular shape that is in a supersonic flow, then it can have various changes in angles. The flow may turn towards the flow or away from the flow, and consequently you can have oblique shocks and expansion fans, a series of them. And across the oblique shocks and expansion fans, the flow is uniform. Only at the oblique shock or across through the expansion fan, the flow is changing. So, this gives us a method to calculate the pressures that is going to be acting on the surfaces of bodies in supersonic flow, and from there, if you know the pressures, you can always calculate the forces, that is the lift and the pressure drag forces of bodies. So, that is what we are going to do in this particular lecture. We will take an example, so this becomes clear to all of you. So, what we are really looking is how the wave patterns form over bodies in supersonic flow. So, if you look at this, a simple example, if you take a flat plate, and put it in a supersonic flow. So, m infinity here is greater than 1 and at an angle of attack alpha, and then for all the streams that are coming on the lower half of this flat plate, this body is actually turning the flow towards the flow. So, a shock wave forms at this point, and this shock would have an angle beta, while on the top surface, if you look at the top surface, all the streamlines coming on top surface, they actually are turned away from the flow. So, they are turned away from the flow. So, you have an expansion fan or an expansion waves are formed here. So, pressure on the top surface P2 decreases because of these expansions, while the shock compresses and P4, that is in this region P4, this increases. Okay. So, it increases in the region 4, and so if you would plot schematically what would be the pressures like in P4 is higher, P2 is lower. So, as a consequence you will get a force in this direction, which can be decomposed into the lift and drag forces. Okay. So, the lift force is here, okay. The drag force much smaller, of course it comes here, drag force is here. Okay. So, the lift and drag forces can be put in this way. So, now this is the way the flow behaves at the flat plate. Now, the flow is going parallel to the flat plate after these expansion fans, and but now when it comes back at the trailing edge, now at the trailing edge the flows come back together. Now, they have different pressures, completely different pressures. It is P4 down here and it is P2 up here. Of course, when it goes back, the flow goes at the end of the trailing edge, they cannot have any pressure difference, because there is no longer a solid surface to sustain a pressure difference. So, pressures have to get equalized. As a consequence of that, you get additional waveforms at the trailing edge. You get a shock here because pressure is lower, it has to get compressed. There is a shock that gets formed here. Okay. So, this you get an oblique shock here, and at the bottom surface you have higher pressures and the pressure has to be relieved or it has to get expanded. You get expansion fans here, and you get a slipstream, essentially a surface which demarcates the boundary between the trailing at the trailing edge between the upper surface and lower surface. The idea here is that it is not always necessary that these two velocities should be the same, but the velocities have to be parallel to each other. So, if you take V5 and V3, they need to be parallel. So, V3 should be parallel to V5 and P3 should be equal to P5. So, this is all the conditions that we can apply at the trailing edge. So, the solving the trailing edge of such bodies involves applying these conditions, that the angle of the flow should remain the same and the pressure should remain the same. Velocities can be different. So, that is why you get a shear or a slip stream, because we are considering an inviscid flow. If you consider viscous effects, it is essentially a shear layer there. Okay. So, but it is an inviscid flow, so it is a slip stream, a discontinuity of velocities. Also of you can have discontinuity in temperatures and densities, pressures have to be the same. So, you can now plot these kind of wave diagrams for several of these kind of configurations. What is plotted here, pressure variation is at the surface. So, this is at the surface, at this particular surface, along the surface. Okay. So, similarly you can plot the pressure variations at the surface for these kind of airfoils are called diamond shaped airfoils. You can see the shape is that of a diamond, and when it is facing a Mach number greater than 1, this is a wedge. So, this is a wedge, so a very small angle. So, this is symmetric about this chord line theta. So, this is turning the flow towards itself, it forms oblique shocks, but at this point it turns away from the flow. So, expansion waves are formed, pressure decreases at 3. So, P3 is less than P2. Then again when it comes back to the trailing edge, you need to give matching conditions for the slip line over here. The flow is parallel to these surfaces. So, now you can see that the flow has to turn into itself in order to become parallel again, and therefore, another set of shocks are formed. So, this can now this angle of attack here is 0. You can consider various angles of attacks, and you can draw such wave diagrams. This pressure variation is on the surface. Okay. So, on the surface the pressure is varying in this fashion. You should always understand that in supersonic flow, what we had discussed earlier in terms of Mach waves and how you have zones of silence and zones of influence. So, unless a Mach wave passes a particular point, pressure does not change. So, if you consider a line here in the free stream, the pressure here remains P1 until this particular point, that is actually well behind the leading edge. So, you can see that leading edge would have passed into the flow, but the pressure will remain P1 until it encounters the oblique shock. Only after that the pressure will change to P2. Similarly, if you go right here until it meets the Mach wave, pressure will remain P2 and gradually it will decrease slowly to P3 until the last Mach wave. Once the last Mach wave leaves, then it becomes P3, it becomes a constant again. So, this one has to understand, as you take different sections in the flow, the pressure variation will be different in the flow according to how the waves move across. So, the wave nature of the flow and how the waves go in a supersonic flow is important, and this will come again and again as we move on in the course. So, here you should understand the forward that is the front portion of these kind of bodies you can always solve using oblique shocks, expansion fans, but the trailing edge, at the trailing edge you should be very careful. You should apply the conditions at P1 that is at the trailing edge. Here the nomenclature is 4 in the region 4. So, P4 upper is equal to P4 lower, they should be the same. These two pressures should be the same, and deflection angles, the velocities have to be parallel to each other. V4u is parallel to the lower surface. These two are the conditions that you can apply at the trailing edge. So, with this let us try to solve one problem. We have a diamond shaped airfoil here, and the angle of this this is the symmetric line. The angle is 10 degrees for this diamond, and it is facing a flow of Mach 3 with an angle of attack of 12 degrees. So, actually this has to be slightly expanded at this region, because you have a 2 degrees of difference, and that is not very well visible in this schematic. So, very small, but this is slightly exaggerated. So, you can, so there is a 2 degree difference here. Okay, so 2 degrees. So, this is 10 degrees, and this is symmetric is 10 degrees, and you have Mach number equal to 3.0. What we are interested in is if the wave structure is so, it has to be like this, because there is a flow turn away from the flow direction here by 2 degrees. So, you have expansion fans here, and this flow again turns the flow away, another set of expansion fans. Here you have an oblique shock, but at this point flow turns away from this direction. So, an expansion fan. Now, they follows different sets of wave structures. So, here you get an expansion fan at the bottom half and an oblique shock at the top half, and finally the flow is turned again to the free stream direction. The idea is what is P4 by P01, and compare P4 by P01 and P4 dash by P01. What is the pressures at these two sides if the wave structure is given is so. How do we solve this problem? So, you have to now put in place together all the concepts you learnt in oblique shocks and expansion fans together. So, we will go and the good thing with supersonic flows is you can go step by step from region 1 to region 2 and solve from region 2 to region 3 to 4, and similarly on the bottom half, because there is a specific directionality involved in supersonic flows. So, let us go start from 1 and go to 2. 1 to 2, region 1 to 2 is an expansion fan region. The way to solve expansion fan flows is to look at the Prandtl-Meyer angle. So, the key equation here is nu 2 is nu 1 plus the change in angle theta, change in angle here. We know theta here is 2 degrees, and we know nu 1 is known because you know the Mach number upstream, which is Mach number is 3. So, nu 1 is 49.757. So, as a consequence you know nu 2, which is 51.757. So, now you have to get back the Mach number. Now, this is a direct plot, Prandtl-Meyer function versus Mach number. You can look at the charts, or you can use a online calculator, and you can get what should be the Mach number if the Prandtl-Meyer angle is nu 2, which is 51.757. It comes out to be 3.105. So, you see that Mach number has increased due to a flow deflection away from the flow of 2 degrees. Now, here when you use charts and tables, you may be off in these numbers by few degrees, 1 or 2 degrees. As a consequence, the answers that you get might be slightly different from between people. This sort of small errors is expected because it involves sometimes interpolation, sometimes reading from a graph, and these kind of operations have small errors. Or you can use online calculators where you can get accurate numbers. Even so, there if you round off, you get round off errors. So, small changes in numbers are expected when we do these kind of numericals. So, that should be borne in mind. Okay. So, what are we interested? Always we should go back to P4 by P naught 1. So, what is P2 by P naught 1? This is P2 by P naught 2 multiplied by P naught 2 by P naught 1. But P naught 2 by P naught 1 is an isentropic flow, there is no change in stagnation pressure. So, P naught 2 is the same as P naught 1. So, I can write this as P2 by P naught 1, and I know what is the Mach number, which is 3.105, and for this Mach number what is P2 by P naught 1 I can get from the charts, 0.232. Okay. So, now moving on from this particular region, we go to from region 2 we go to region 3. From between region 2 and region 3, it is again another expansion fan. Same principle holds good, nu 3 is nu 2 plus delta theta. Change in the angle. What is the change in angle? Trigonometric relations. If you use trigonometry, this is 10, it is symmetric, this is 10. So, this angle has to be 20 degrees, is from trigonometry you can find that out. Okay. So, delta theta is 20 degrees. So, we know what is nu 2, we had just found out 51.757. So, nu 3 turns out to be 71.757. Corresponding Mach number M3 is 4.49. So, now we need P3 by P01. Again P3 by P01 is the stagnation pressure has not changed either in region 2 or in region 3, isentropic flow. So, directly you can find P3 by P01 for 4.49, which is 0.003498. Now, between region 3 and region 4, now that region there is an oblique shock. So, it is an oblique shock. Now, the flow totally has deflected by 2 degrees and 20 degrees. And at the end, at the trailing edge, the flow returns back to the angle 0. Okay. So, the free stream angle. So, the flow has to turn towards itself by 22 degrees. So, region 3 to 4, the flow deflection is theta is 22 degrees towards itself. So, it forms an oblique shock. Mach number is 4.49. Okay. So, now use the m beta theta charts, find out what should be beta, and it is 33.3 degrees. Okay. So, now from this, now what we have to do, we know beta. So, we find Mn3 is M3 sin beta and apply normal shock relations for M3 which is 2.465. Okay. And also that you will get Mn4 from here, Mn4 and you get Mn4 and Mn4 from Mn4 you can get M4. M4 is Mn4 by sine beta minus theta. All of this from normal shock relations you will get Mn4 if you know Mn3, and from here we can get M4. M4 is 2.63. so obviously the Mach number has reduced. So now what do we need here? We need P4 by P01, P4 by P01. This is what is required. This can be P4 by P3 multiplied by P3 by P01. P4 by P3 is the pressure ratio across the shock, which you know here. Mn3 you know. From this you can find out what should be the pressure ratio across the shock. 6.916 multiplied by P3 by P01, 0.003498, and this turns out to be 0.024. okay, so bear in mind 0.024. okay. Now we look at the lower side. What happens in the lower side? So lower side you have started off with the shock, so it is something like this nature. There is a shock here and the flow from the initial has deflected by 22 degrees. Oncoming flow Mach number is 3.0, and so beta for this shock wave angle beta, so theta is known, beta is 40.19. so this angle is 40.19. okay. So now we know beta, so we can find out what should be Mn1 is M1 sin beta. okay. Once you find out Mn1, this is 1.935. all properties of the shock like P2 by P1 can be found out. It is 4.2015 by using normal shock relations, normal shock charts or calculators. You can find these numbers, and what we need again is P2 prime by P01 is P2 prime by P1 multiplied by P1 by P01, and P1 by P01 is nothing but for the upstream Mach number M equal to 3.0. what is P1 by P01? This is known, 0.02722. so this value is 0.1143. and what is the Mach number? So you go M2 prime is Mn2 by sine beta minus theta, 5899 by sine of beta 40.19 minus 22. this is turns out to be 18889. okay. So now we go from region 2 prime to 3 prime on the lower side. Here it's an expansion fan, delta theta is 20 degrees. You start off with M2 prime of 1.889. okay, and here nu 2 prime, for this nu 2 prime is 23.019 degrees. so nu 3 prime then is 43.019 degrees. so M3 prime turns out to be 2.71. so we can find out what is P3 by P03. Your stagnation pressure is going to be constant across the expansion fan. okay. and we need P3 prime by P01, which is P3 prime by P03 multiplied by P02 prime by P2 multiplied by P2 by P01. we have got P2 by P01 here, and we know Mach number is 1.889. So we can find out what is P02 by P2 prime, that can be found out. P02 is equal to P03. So P3 prime by P03 can be known from, it is given here. Can do the multiplication, this turns out to be 0.03184. Now at the final point between 3 prime and 4 prime, it is an expansion fan. So M3 is 2.71 from the calculations, and here the flow turns away by 2 degrees. So it turns away by 2 degrees. So nu 3 is 43.019. So nu 4 is 45.019, which is nu 4 is nu 3 plus delta theta, which is 2 degree here. So M4 is 2.77. Okay, and we need P4 prime by P01. Okay, this is P4 prime by P04, P03 dash by P3, P3 dash by P01. So these were calculated in the earlier steps. P4 by P04, you know 2.77. So for this Mach number, P4 by P04 is 0.03857. If you do the multiplication of all these numbers, you get P4 prime by P01 is 0.029. P4 by P01 in previous calculation was 0.024. They are very close to each other. We need so the idea is that the pressures P4 prime should be equal to P4. We have of course the round off errors slightly, but even considering them, these are very close to each other. Okay, so it actually satisfies this relation P4 prime equal to P4. Now if you know the pressures at each surface, you can always calculate what is the force. Pressure multiplied by area is a force. So you know pressure, you have found out pressure at each surface now, and from here you can calculate what is the force. So force acting can be calculated at each surface, and then they can be resolved into parallel and perpendicular components, and therefore you get lift and drag. So this way of doing these kind of sort of estimating the forces is known as the shock expansion method. Okay, I hope this elaborate example has given you an idea of how to use shock waves and expansion wave relations to solve certain problems. We will solve more problems down the line in the next few classes.